Okay, so in the last lecture we had discussed about heat conduction. So we had seen that when a longitudinal shaped heat conductor with uniform cross-sectional area is in steady state, okay, such that the two ends are maintained at temperatures T1 and T2 constant with some insulation from the outside so that heat conducts only along the length of the conductor. Then we had seen that rate of conduction at steady state the two important parameters were heat current or rate of conduction, which becomes this, and a uniform temperature gradient through the conductor, which becomes this much. Okay. The next thing based on this we had understood we can relate this with heat current and thermal resistance. So this is equivalent to a situation where we can think of temperature in the same way like we think of potential, and we can think of rate of conduction as the same thing as heat current. So heat current becomes temperature difference divided by thermal resistance, where heat current is equal to delta Q by delta T, and thermal resistance is L upon Ka in Kelvin per watt. Whereas K was thermal conductivity of the material in watts per meter Kelvin. Okay. So this becomes a very useful formula or a useful way of relating this situation, especially whenever we have combination of conductors. So we had seen series and parallel combination of conductors and how to relate this. Okay. So let's do a practice question based on this today. So all this that we are discussing right now is part of your upcoming test portion. So make sure you revise the practice questions we are doing in this part of the lecture today, the conduction part, for your upcoming test. Okay, so in our next example, what we have is a combination of thermal conductors, okay, which looks like this. So this is a combination of 6 metallic rods which are isotropic and insulated from outside. So these rods are of length L each, and thermal conductivity K1 and these other 3 are like this. So given that K2 is equal to 3 times K1, if temperature at A is maintained constant at 120 degrees C and temperature at B is maintained constant at minus 60 degrees C, then find this thing, temperature at C at steady state. And second, given that K1A by L, or rather L upon K1A, equals to, let's say, 240 Kelvin per watt. Find the net rate of heat conduction at steady state between A and B. Okay, so just try this question out, people. So you have to convert this into an equivalent circuit and convert each of the rods into an equivalent heat conductor or thermal resistor, and use the combination of resistors concept over here, like we discussed in the previous lecture. So this is a very important type of question from heat conduction at the NEET level. Okay, so let's understand the method for doing this type of question is to convert this into an equivalent circuit diagram first. So let's also label all these points. Now, if we take this quantity L upon K1A, which is given to us later as 240 Kelvin per watt. But if we take this as R1 suppose, then L upon K2A, which is R2, is equal to R1 by 3, because given to us that K2 is equal to 3K1. Okay, so we can see our equivalent circuit becomes like this. Now in this circuit, these resistors are R1, these three, okay, whereas this resistance is R2 and this is R2 by 2, because the length is also half. Okay, so what we can do is we can take R2 as some 6R, therefore R1 is, sorry, let's take R1 as 6R. Okay, so R2 is equal to 1 by 3 R1, that will become 2R, and R1 by, sorry, and R2 by 2, these two resistors in between will become R. So that will make the solving part easier. So wherever we had R1, we will replace it with 6R. Okay, so these were the three R1s. Then wherever we have R2, we will replace it with 2R. Okay. And wherever we had R2 by 2, we will replace it with R. Okay. So this is our equivalent circuit now. Okay. Now we know that temperature at A is 120 and temperature at B is minus 60. So solve the circuit next further to find the temperature at C. So I've given you a hint on how to proceed over here. Now just try this out. Surveys, that is an assumption. I'm not saying it is 6R, but you can see here na, ki I have resistor R2 which is R1 by 3, and I have resistor R2 by 2 which is R1 by 6. No? So it is best to take them in that kind of ratio. No? The important thing here is that the ratio of this resistance R2 is to R1 is 1 is to 3. No? Understood how that came? No? Because K2 is 3 times K1, and then we have R2 by 2. So it is more convenient to take R1 as 6R, so that we get these two as 2R and R. Understood now? No? Okay. So that's just a matter of convenience. Okay. Now next thing what we can do here is first of all convert this into an equivalent circuit. So we can see that you can let this be. Okay. You can let this be. But first of all convert this into a series combination of R plus 6R plus R. So that is 8R. So now we can understand that because there is a parallel combination breakup over here, so whatever current I is coming here, if this current is I1 and this current is I2, you can see that 8R into I1 will be equal to 2R into I2. So I1 is to I2 will be 1 is to 4. Okay. And I1 plus I2 is equal to I. Okay. So I1 will be 1/5 of I. So this becomes an important equation. Okay. Now next up you can see that this can be further written as 6R in series with parallel combination of 8R and 2R, that is 1.6R. Okay. So TA was how much? 120, and TB was minus 60 degrees C. So now we can first of all see that this current I, okay, so the equivalent resistance across AB becomes 6R plus 1.6R plus 6R, so 13.6R. Okay. So the current I will become TA minus TB divided by equivalent resistance. So 120 minus 60 divided by 13.6 R. So 180 divided by 13.6 R. So that then write 180 by 13.6 as, let's divide by 4 first. 45 divided by, doesn't value that much, but anyway. Okay. So this is the equivalent current. So just make a note up to this portion first. Then we'll see how to find the temperature at that point C. So now look very carefully what we will do. We will substitute this value of current in this diagram first to find temperature at the point F. So we can see that temperature at F minus temperature at B divided by 6R should be equal to this current I. So temperature at F is unknown, but temperature at B was minus 60 divided by 6R should be equal to 225 divided by 17R. Okay, so from this we can see that temperature at F will become 225 by 17 into 6 plus minus 60. Okay. This we are applying Ohm's law across the conductor F. Across FB, we are applying Ohm's law. Okay. So from this we have found the temperature of the point F, which will come out to be, just write it down for you. So this will come out to be about 19.41. Okay. Then we will apply this same concept for conductor CF. Okay. So you can see for conductor CF, the current I1. Now I1 from here was how much? 1/5 of I. So from below it becomes 1/5 of 225 by 17 R. It becomes 45 by 17 R. Okay. So therefore temperature at C minus temperature at F divided by R should be equal to I1. So same principle we are applying again. So temperature at C is unknown, but this is 19.41 upon R. This should become our I1, which is 45 by 17 R. So now you can see temperature at the point C will become 19.41 plus 45 by 17, which will be roughly 22.06. So this becomes the first part's answer. And second part's answer, we have to just plug in the value of R given to us. From the value of L upon K1E. We have to plug in the value of R. And from that, we will get the net rate of heat conduction, which is I. No, the answer for current will be same service. The numerical answer will be same because ultimately you are substituting. रेशियो ऑफ रेजिस्टेंस इज सेम है ना बेटा, तो assumption से क्या फर्क पड़ता है. Okay, so this is clear now. Now next thing, see, we have to find, so L upon K1A, that is our R1 is given to us as 240. So from that we have to find the equivalent heat conduction across AB. So see, we have already seen that R equivalent is 225 by 17R, where we had seen that R1, which was 6R, was equal to L upon K1A, which is given to us as 240 Kelvin per watt. Okay, so that means R is 40 Kelvin per watt. So now we will substitute this here. So equivalent R is becoming 225 divided by 17 into 40. So now, sorry, equivalent R was not this, this was I equivalent. Directly this I is equal to 225 by 17R. So current I is what we wanted to find out. So that's it. We have our answer. I is in watts now. So both the parts are solved using that same concept now. So this is delta Q by delta T net across AB. So this is the answer to the second part of the question. This was the answer to the first part of the question. So these type of questions are important, which are more about basically applying Ohm's law and circuit theory. But in this case, we call it a thermal circuit. Instead of an electrical circuit, it's a thermal circuit. Okay, next up, we were looking at, in the previous lecture, we were also looking at applications of integration. In thermal conduction. Okay, Sarvesh, shall explain that again. So we'll come back to this. ये EF के across जो resistance है देखो सर्वेश, we converted this to this formula. You're following now? So resistance across EF is parallel combination of 8R and 2R. This is clear? Why it is parallel combination? From this diagram you can see. Right, very good. So parallel combination का formula क्या होता है? 1 upon REF is 1 by 8R plus 1 by 2r. So just use that now. Okay. One plus 4. So got it now. You just use this formula that 1 upon R equivalent is 1 by R1 plus 1 by R2 for parallel combination. Okay. And R equivalent is R1 plus R2 for series combination. Okay, okay. Understood. Okay. Or you can also, in case of two resistors, you can use the direct formula that it is R1 R2 upon R1 plus R2. That's how I had done it initially, actually fast. So you can see 8 2s are 16 divided by 8 plus 2 10. So 16 by 10 is 1.6. So when you have only two resistors in parallel, you can just quickly use that formula R1 R2 divided by R1 plus R2. Instead of first calculating the reciprocal and then again reciprocaling it, you can just use that. Okay. Okay. So let's come back to application of definite integration. So we had seen an example last time where we had variable K on non-uniform thermal conductivity, or what we call an anisotropic material. Now today we will see a slightly different situation. Okay. So we'll see a situation where we are looking at thermal conduction through a non-uniform cross section. So we have a conductor whose cross sectional area is non-uniform. So first and most direct obvious example of this is conduction through a frustum shaped conductor. So what is a frustum? It is a section of a cone. We take a cone and cut a section of it. That is the frustum of a cone. So imagine we have a solid metallic cone which we have cut from one side a bit. So it's not ending in a so this is a solid metallic frustum. Okay. So frustum of a cone is this kind of a shape. So we have a cone like this and now we cut the cone into a section like this. So then what we are left with here, this is a frustum of a cone. Okay, so that kind of thing we have. Okay. And as usual, we are insulating it from outside so that there's no heat transfer from the outer surface. Plus, we are keeping this in a constant temperature reservoir. If you want to see how we can calculate the rate of thermal conduction, okay. So this is maintained at temperature T1, this is maintained at temperature T2, and we want to find out the, okay. So this frustum is made of metal which has thermal conductivity K. Okay. It has axial length L, okay. And it has base radii A and B. Okay. So it's like this radius, this diameter is 2A, this diameter is 2B, and this length is L. So this axis of the frustum this is the axis. So the axial length is this one. So that kind of thing. So we want to find the thermal resistance for the metallic frustum in the above situation. And we want to find the heat current. At steady state. Assuming that T1 is greater than T2, of course. So just take down the question first, we'll discuss next. You better pay attention with that ना. Radius is obviously a ना, तभी तो उसका diameter 2a है ना राइट. जो डायग्राम में मैंने दिखाया है वो तो डायमीटर है ना बेटा. सो रेडियस तो उसका हाफ हुआ ना. See, this thing is 2b. Okay, so this is what? This is the diameter of the base, no? Yeah. Okay, now let's understand how to do this question. So as you can see, the application of integration comes in because we cannot use L upon K into area directly because the area is not uniform. Had it been a cylinder of radius r, we would have directly used the formula L upon K into pi r square. But here we can't do that because it's not a cylinder, it's having a variable area of cross section. So what we'll have to do here is we'll have to use integration wherein now the heat conduction is happening along this axis. So we will at some distance x from this side, we will slice a thin disc like this, which is of thickness dx and which itself has radius r. Whereas here you can see the radius is a. Here you can see the radius is b. Okay. So you can understand that the radius is varying with the x coordinate like this, like I'm showing next. The radius is equal to a at x equal to 0 and the radius is equal to b at x equal to L. So in between at some point how we'll find the radius? At some general x like this, you can see that r minus a upon x is equal to b minus a upon L. So r is equal to you can see that there is r varies linearly with x. Okay. So for now we can see that for this differential section, okay, which is a disk of radius r and thickness dx, the thermal resistance is this, where r is this. So now for the frustum, the equivalent resistance will become this, because all such sections from x equal to 0 to x equal to L are in series combination. So we are doing the summation by integration. So equivalent resistance will become this integration, where R is equal to this kind of relation. Okay. So just note down up to here, and then next we'll see how to do the substitution and complete the integration. So the substitution is a little complicated. There's a trick method of doing it. I'll explain that next. Okay, now let's understand how to do this integration. So it looks a bit complicated, but actually it's not. So the method of substitution is important now. So for the substitution in the integration, we'll use this. So we'll see that since r is equal to like this, so we can substitute dr if you differentiate both the sides into dx. So we can now invert this. So you can say dx is L upon b minus a dr. So we will substitute dx in the numerator of the integration. Okay. So the integration will now become, just substitute dx in the numerator as this L upon b minus a into dr. Okay. And this limits become x equal to 0 corresponds to r equal to a, and x equal to L corresponds to r equal to b. So that you can see over here. X equal to 0 implies that r is equal to a, and x equal to L corresponds to r equal to b. So this becomes, now take all the constants outside. So dr by r square. So that now becomes a very simple integration. Minus 1 by r from r equal to a to r equal to b. So finally we end up with this simple solution that L is equal to, R is equal to L upon K into pi AB. Okay, so just make sure you understand the steps of the integration, substitution in the integration very carefully here, and then the application of definite integration with the substitution of limits also. And next up, we will substitute this value of equivalent thermal resistance directly in the problem to calculate the heat current or the rate of conduction delta Q by delta T. Yeah, Sarvesh, the first step of substitution. देखो यहाँ पे क्या है, R is equal to a linear function of x. It is some mx plus c kind of term where m is b minus a by l and the constant is equal to a. So now differentiate both the sides. So dr by dx is m because m is a constant. So that is b minus a by l. So therefore we can substitute dx as l upon b minus a into dr. So this is what we substitute in the integration. And the numerator is dx. अरे ये ना इसको डिफरेंशिएट करो x के टर्म्स में, dr by dx is what, d by dx differentiation of mx plus c. So m and c are constants ना, तो ये क्या आएगा, m आएगा कि नहीं, और m का वैल्यू कितना है यहाँ पे, this is the easiest type of differentiation to do ना, linear function differentiation is a constant. Is it clear now? Okay, good. So with that we complete today's session, and we've completed most of heat conduction. So up to what we've discussed today is relevant for your test coming up on Sunday, whereas next lecture we'll be picking up radiation, which will not be part of the common test coming up on Sunday. So make sure you practice questions from heat conduction along with questions from application of first law of thermodynamics that you've done before, and also applications of this thing, calorimetry and thermal expansion, etc. done before that. Kinetic theory of gases, first law of thermodynamics, that's the most important part, along with that heat conduction. And of course, the easy first part that we had seen of thermal expansion and calorimetry. So all this is important for your upcoming test. So that's it, and wish you all the best, people. Okay, Aruja, I will send a list of questions from HC Verma for you.